Central limit theorem. The central limit theorem is one of the most important theorem in statistics, and it might be a little bit hard without an explanation. Let's see one example. It will make it easier to understand. Suppose a machine in a dress factory is set to cut silk material exactly to the length of 1000 millimeter. Is it possible to cut each piece to 1000 millimeter exactly? Not really. Using a machine, you cannot save each time 1000 millimeter. So on our example over here, you can see that say that we have 1000 millimeter and other pieces are around 1000 millimeters. So in our example, we have the standard deviation set as sigma is equal to 12, and we have the mu is equal to 1000. Each time we cannot have 1000 millimeter, but we can have close to 1000 millimeters somehow. So experience tells us that if we have a properly operating machine, cuts millions and millions of pieces, lengths of these pieces build into a slope close to normal distribution like this. As you can see, this is gonna be built to slope close to normal distribution. Now let's suppose from these millions and millions of pieces, we randomly select a sample of 36 pieces. And we know that the sample average approximately equal to sample average was shown with the X bar approximately equal to population average, and sample standard deviation also approximately, I should write down approximately symbol over here and over here, approximately equal to population standard deviation. So if we have the X bar, which is the average length of the 36 pieces in our sample, say 998 millimeters. So we picked 36 samples in our from our population, and we got the average value is 998 millimeters. So it's somewhere here. We picked another one, and it came up as 999,000, 1001, 1002, and then another one picked another one, 999.5, 1000.5. We continue picking these samples. So since we know the sample average should be approximately equal to population average, you can ask yourself then, when I picked 36 pieces of sample from my population and I got 998 as my sample average, would you consider 998 millimeter approximately equal to 1000 millimeter? In other words, you can ask this question to yourself: how close must X bar be to be considered approximately equal to population average, mu? To answer this question, we need to randomly select thousands and thousands of samples. with each sample containing 36 pieces of material cut from the machine. As I showed over here, I picked thousands of 36 pieces of samples. And for each sample of 36 pieces, we calculated the average over here, some averages I have. Now we have thousands of sample averages. Now let's look at another picture. We have thousands of sample averages in between around like 996 and 1004. Now we can answer the question: how close does sample average have to be considered approximately equal to mu? Almost every sample average fell between 994 and 1006 millimeter. In fact, most of the sample averages clustered between 998 and 1002. So it is pretty close, approximately pretty close to 1000 millimeter. In another thing, when you take these sample pieces from our population, 36 samples, and when you take the averages, you see that we have a bell-shaped curve, normally distributed curve. Now we can talk about a theorem. If all possible different samples of a fixed sample size n are drawn from a normally distributed population with mean mu and standard deviation sigma, then the distribution, which is sigma x bar, will be normally distributed with mean mu and standard deviation sigma over square root of n. So if we have mu is our mean and standard deviation is sigma over n, in our previous example, the example which we gave at the beginning, what we have, mu is equal to 1000 millimeter, sigma is equal to 12. So our new standard deviation is gonna be calculated as sigma over square root of n. So we have sigma is given 12. We have 36 samples. When we do this calculation, we have 12 over 6, which is 2. So let's do an example. Let's see. Let's look at an example related with this one. A machine in a dress factory cuts pieces of silk material to an average length of mu is equal to 1000 millimeter with standard deviation sigma is equal to 12 millimeter. If one day we take a sample size n is equal to 36 pieces and calculate the average length of these 36 pieces and discover the sample average x bar is equal to 995 millimeter, find the z-score associated with x bar is equal to 995 millimeter. So let's go back and what we said, let's look at our theorem. We said mean is equal to mu. So our sample, we can say that mu x bar is equal to mu, and our sample standard deviation is equal to sigma over square root of n. So using these, we can write our z formula as x bar minus mu over sigma x bar. So this is going to be equal to x bar minus mu divided by sigma over square root of n. So let's go back to our question. In our example, we have, let's write down what is given. Mu is equal to 1000. We already calculated, but let me calculate again. X bar, sigma x bar is equal to sigma divided by square root of n. My sigma is in the question given 12 millimeter divided by square root of 36, which was calculated and we got 2 millimeter. Therefore, we can find x bar is given to us as 995. Let's put these in our formula. Z is equal to x bar minus mu divided by sigma x bar. X bar is 995 minus mu is 1000 divided by 2. And when we do this calculation, when you put this on your calculator, you will see that you will have negative 5 over 2, which is equal to negative 2.5. So you can say that the Z score for simple average x bar is equal to 995 is equal to negative 2.5. Now let's give our central limit theorem. Central limit theorem say that if all possible different samples of a fixed sample size n are drawn from a population of any shape with mean mu and standard deviation sigma, then the x bar distribution will be normally distributed with mean mu and standard deviation sigma over square root of n, provided the sample size n is greater than or equal to 30. That's provided n is greater than equal to 30. In this central limit theorem, you see that the x bar distribution will be normally distributed, and the mean is gonna be, mean is our sample mean is equal to mu, and sample standard deviation is equal to sigma over square root of n. So how can we apply this central limit theorem to an example? Let's look at an example. The National Institutes of Health agreed to supply active disease viruses to research firms for the purpose of experimentation. A process is set up to automatically fill millions of small test tubes to an average of 9 milliliters of disease virus with standard deviation 0.35 milliliter. If we continually take random samples of 49 test tubes in each sample and calculate the average fill between what two values would you expect to find the middle 99% of all the sample averages? So over here we have the average is 9 millimeter, standard deviation is 0.35 milliliter, and we have 49 samples, and we are looking for, we are given the area 99%. So it is a classical working backward question. So when we write down, I always suggest you to write down the given, what is given. Average, sample average, average is equal to 9 given to us, and standard deviation is given to us 0.35, and n is given to us 49, and we have the area is given to us which is 99%, or which is equal to 0.99. So if we have 49 test tubes, therefore we can use the central limit theorem. So we have a population, and we have some population, and we got sample of 49 test tubes, and we got the average is mu is equal to 9 milliliter, and we are given sigma. This is my mu. Sigma is given 0.35. We need to find sigma x bar. Sigma x bar is calculated by sigma divided by square root of n. So sigma is 0.35. Square root of n is square root of 49. When we do this calculation, we end up with 0.35 divided by 7, which is going to give us 0.5 milliliter. We got our sigma x bar. Now, we also given that the area 99% over here, 99% almost over here, maybe very close to here. We have 99% part is given, and we want to find the z-scores over here. In between, we want to find the z-score first, and we will get the values over here, sample averages. So first of all, as we said, we need to find the z-scores. How are we going to find the z-scores? Remember, z-score table is giving us the area between 0 to z values. So in order to find the z value over here and over here, we need to calculate the half of 99%, which is equal to, if we calculate the half of the 99%, you see that this part is equal to 49.5, and this part is equal to 49.5. On the z-score, 5%, by the way, percent. On the z-score table, if you look at the 0.495, you will see that the value for z is going to be equal to 2.58. You will see this value on your z-score table, and on the negative side, it's going to be negative 2.58. So what am I going to do with these z-scores? I can be able to now use my z formula. So z is equal to x bar minus mu over sigma x bar. So I know my z on the left is negative 2.58 is equal to x bar, I don't know, that's the unknown value, minus mu is 9, divide by, we already calculated our sigma x bar, which is 0.5. When you do this calculation, you will see that you will end up with x bar is equal to 8.87 milliliter. Also, when you calculate the right side, you will see 2.58 equal to x bar minus 9 divide 0.5. When you calculate, when you do cross multiplication and add both sides 9, you will end up with x bar is equal to 9.13 milliliter. So this is saying that if we continually take random samples of 49 test tubes in each sample, and calculate the average fill in each of these samples, then 99% of all the sample averages would be expected to fall between 8.87 and 9.13 milliliter. My last example is here. I think I made a mistake over here. Brels, I was gonna write down Brels. Brels shampoo is marketed along with various other shampoos through a large national chain of convenience stores. In these stores, Brel's market share has remained relatively constant at mu is equal to 24, which means that on an average, 24% of the shampoo sold in these stores is Brel, with standard deviation 3.20. If we continually take random samples, each consisting of 64 stores, and calculate the average market share for each sample, what percentage of sample averages would you expect to have a market share less than 23.80%? So again, what is given to us? First of all, let's look at that stuff. So we have given mu is equal to 24, and we have given standard deviation is equal to 3.20, and we are looking for the market shares less than 23.80. So how are we gonna find the less than 3.80 parts? Well, it would be helpful if we have a if we make a picture. We have lots of stores and stuff, lots of stores here, and we have the samples and sample averages over here, and we have 24 is my mu is equal to 24, and somewhere here is 23.8. Somewhere here is 23.8, and we are looking for the area less than 23.8 parts. So in order to find that area, first thing we need to do is we have to calculate the z-score value. Let's calculate our z-score. Z-score is calculated by z is equal to x bar minus mu divided by sigma x bar. So z is equal to x bar is 23.8 minus my mu is 24 divided by let's see what is going to be here, sigma x bar. Let me calculate sigma x bar on the side. Sigma x bar is equal to sigma divided by square root of n. So in my case here, 3.2 divided by square root of 64 stores. We have 3.2 divided by 8, which is equal to 0.4 market share. So I instead of sigma x bar, now I can write down 0.4. When you do this on your calculator, you will see negative 0.5. So negative 0.5 is our z-score. Now, when we look at our z-score table, we can find the area between, so this is, let me write down 0, this is negative 0.5. When we look at the z-score table, we can see the area between 0 to negative 0.5. When you look at it, you see that 19.15% is this area with the green. But we are looking for the area with the blue, this part. How can we find that? We know that normal distribution is symmetric, so we can, if we do 50% minus 19.15%, we will have 30.85%. If we continually take random samples, each consisting of 64 stores, and calculate the average market share for each sample, then we see with our calculations 30.85% of all the sample averages would be expected to have a market share less than 23.8. Now you might wonder that if the central limit theorem applies to any shape of population. Yes, central limit theorem is applying to any shape population. The X bar, the sample distribution, the X bar will distribute normally around mu for any shape population, provided n is greater than equal to 30. If you have a, for example, a population like normal distributed, so you will have a normal distributed with R mean here. If you have a population like this, you can have a normally distributed one, X bar distribution. So if you have a population like this, you can find the X bar distribution over here. So this is my population. This is my population. This is the population also. If you have a population like this shape, you can still have a normally distributed, provided n is greater than 30, greater than or equal to 30.